Hey, I hope I'm audible to all my students who are attending this practice lecture for the Mathematical Methods for Economics course. In this particular practice lecture, I'm going to start with the discussion of practice problems of a very important module called multivariable optimization. If students have attended my lectures on multivariable optimization, recall it is one of the very important topics we cover up in our mathematical methods for economics course. It makes use of the concept of partial derivatives. We have done good practice of partial derivatives before as well. Now, in this particular lecture, let me quickly start with, let me quickly give a brief of, how to maximize or minimize a function in several variables. And let's also do a couple of practice problems based on this concept. So formally in this lecture, I'm starting with practice problems on multivariable optimization. So let's quickly start with this particular practice lecture. First of all, I'm just writing the main heading. We are looking at practice problems based on practice problems based on multivariable optimization. Multivariable optimization. Okay, so I'm quickly revising with all students the first order conditions and the second order conditions for multivariable optimization. So recall the first order conditions in case of two variables. We have done this theorem in our lectures on multivariable optimization. I'm quickly revising it in this particular lecture just for clarity. Okay, so a necessary condition for a differentiable function, a necessary condition for a differentiable function f of xy to have a maximum or a minimum at an interior point. Let me write this more clearly: to have a maximum or a minimum at an interior point say x0 y0 of its domain is that f of x is that x0 y0 is a stationary point. X0 y0 is a stationary point of the function f. That is, what does this mean? A necessary condition for the function f of xy to have a maxima or a minima at the point x0 y0 is that x0 y0 should be the stationary point of the function f. What does it mean? It means that f1 dash at x0 y0 should be equal to 0 and f2 dash at the point x0 y0 should be equal to 0. If the first order derivatives at the stationary points x0 y0 are equal to 0, then I can say that x0 y0 qualifies to be either a maximum or a minimum. That means whenever you have to find a maxima or a minima for a function in several variables, what's the first step we do? We put the first order partial derivatives equal to 0. We put the first order partial derivatives equal to 0 and we solve the equation simultaneously to find the stationary point x0, y0. And then let's look at the second order conditions. So I can now write what are the second order conditions, or I can say the second derivative test. So recall the second derivative test. Recall the second derivative test for functions of two variables. Again, where I've covered this in my lectures on multivariable optimization. So let f of xy be a function with continuous partial derivatives, of the first and second order in the domain S, and let x0 y0 be an interior point of S that is a stationary point of F. That is a stationary point of F. So for conducting the second derivative test, we are going to first of all find out the stationary point. How do I find the stationary point? By putting the first order partial derivatives equal to 0. I get the stationary point, which is also the interior point lying in the set S, where S is nothing but the domain of the function f of x. The domain of the function f of xy is called the set S. The interior point called x0, y0 will lie in this domain S and is the stationary point which we get by solving the first order partial derivatives. Now, I am erasing the initial part and quickly revising how to work out the second order derivative. So if I erase this part off, erasing all this off, I can write, let me continue with the explanation from here. So I can write let A be equal to f double one double dash x0 y0, which is the second order partial derivative of the function with respect to x evaluated at the stationary point x0 y0. Okay, first of all let C be equal to f double two double dash x0 y0, which is the second order partial derivative of the function with respect to y evaluated at the stationary point x0 y0, and let B be f1 2 double dash x0 y0, which is the second order cross partial derivative of the function evaluated at the stationary point x0 y0. Now, by now, students should be comfortable with the notations because I've used these notations several times in my main lectures on multivariable optimization. I believe that students who are watching this lecture are comfortable with multivariable optimization lectures, which I have done in depth. Okay, so f double one double dash is the second order direct partial derivative of the function with respect to x. F double two double dash is the direct second order partial derivative of the function with respect to y, and f1 2 double dash is the second order cross partial derivative of the function. And all these are evaluated at the stationary point x0 y0, which I have found by solving these two equations. Okay, now if A is less, this is point number 1, if A is less than 0 and AC minus B square is greater than 0, I can say that the stationary point x0 y0 is a local maximum point. Is a local maximum point. Case 2. If A is more than 0 and AC minus B square is also more than 0, I can say that the stationary point x0, y0 is a local minimum point. Is a local minimum point. Case 3. If AC minus B square itself turns out to be negative, then the stationary point x0, y0 is a saddle point. If our AC minus B square is negative, the stationary point x0, y0 is a saddle point. And then let's see what happens if AC minus B square is equal to 0. So if I erase all this off, if I erase this part off, I can write that if, and the fourth case, which is as follows, if AC minus B square is exactly equal to 0, then the stationary point x0, y0 could be a local maximum. It could be either a local maximum or a local minimum, or it could even be a saddle point. I have done all these cases in my main theoretical lectures on multivariable optimization. In this particular practice lecture, I am just quickly revising them before I jump to numericals. I am revising it again with all students. We have looked at how to find the stationary point. So step number 1, when you are given a function in several variables, step 1, you put f1 dash and f2 dash equal to 0. You put the first order partial derivatives equal to 0. You get your stationary point x0, y0. Once you have obtained the stationary point x0, y0, to check whether it's a local max or a local min or a saddle point, we work out the second order partial derivatives, which are A, C, and B. And then we just look at the criteria. If A is negative and AC minus B square is positive, we conclude that the stationary point x0, y0 is a local maximum point. If A is positive and AC minus B square is positive, we conclude that the stationary point x0, y0 is a local minimum point. If AC minus B square is negative, we conclude that the stationary point x0, y0 is a saddle point. And if my AC minus B square is exactly equal to 0, we conclude that we cannot form any conclusion in that case. So we can say that it could either be a local max or a local min or a saddle point. Now, this AC minus B square is nothing but a Hessian matrix. It's a Hessian matrix of 2 cross 2 order. Okay, so if students are wondering, this AC minus B square is nothing but A, B, B, C. If I evaluate this determinant, it's AC minus B square. So it's a Hessian matrix of all the second order partial. Okay, now after having revised all this theory, let's now jump to some numerical problems. So I am erasing all this off. Okay, and let's look at question number 1 for practice. Determine the extreme values. Determine the extreme values of the function z, which is equal to x square minus xy plus y square plus 3x minus 2y plus 1. So we are given this function and students can clearly see it's a function in two variables x and y. Okay, now we need to first of all find out the stationary points. Now how do we do that? We put the first order derivatives equal to 0, first order partial derivatives. So del z by del x equal to 0 implies if I partially differentiate the function with respect to x, remember I am treating y as a constant. So it's going to be 2x minus y plus 3 equal to 0. That's my equation number 1. And equation number 2 is I put del z by del y equal to 0. Remember, when I'm partially differentiating z with respect to y, I treat x as a constant. So it's minus x plus 2y minus 2 equal to 0. This is equation number 2. Now we need to solve equations 1 and 2 simultaneously. That's pretty easy. Equation 1 is 2x minus y equal to minus 3. I can write it like this by taking 3 on this side. And equation 2 is minus x plus 2y equal to 2. I take minus 2 on this side, becomes 2. I can solve these two equations using the method of elimination. I multiply this by 1, I multiply this by minus 2 to make the coefficients of x equal. So I get 2x minus y equal to minus 3. That's my first equation. The second equation is 2x minus 4y equal to minus 4. Call this as equation 3. Call this as equation 4. Let's subtract equation 3 minus 4. So 3 minus 4 would mean 2x and 2x cancel out. Minus y minus of minus 4y is equal to minus 3 minus of minus 4. So I get minus y plus 4y is equal to minus 3 plus 4. 4y minus y is 3y. 4 minus 3 is 1. So I get y as 1 over 3. Once I got the value of y, plug it in any of equations 1 or 2. Suppose I put it in equation 1. So 2x minus y is 1 by 3 plus 3 is equal to 0. So 2x is equal to 1 over 3 minus 3. So this implies that 2x is equal to 1 minus 9, which is minus 8 by 3. So my x is going to be minus 8 by 3 divided by 2, which I can also write as half. So x comes out as minus 4 by 3. So I've got x as minus 4 by 3 and y as 1 by 3. These are my stationary points. So I can erase the initial part. Let me erase this particular part, the solving part. And I can write that the stationary points are x equal to negative 4 by 3 and y equal to 1 by 3. Now, once I have found out these points, we can work out the second order derivatives to classify whether it's a max or a min or a saddle point. So I find out A. A is nothing but fxx. It's nothing but del square z by del x square. This is already del z by del x. Can I further differentiate this with respect to x? I get 2. It's positive. Let's find C. This is fiy, which is del square z by del y square. Del z by del y is this. If I further differentiate this with respect to y, I get 2, which is again positive. And B is nothing but fxy, which is del square z by del x del y. That means del z by del x, I differentiate with respect to y. The derivative of 2x minus y plus 3 with respect to y partially is just minus 1, which is negative. Let's find AC minus B square. So A is 2, C is 2, B is minus 1 squared up. So it's 4 minus 1, which is 3, which is positive. So if I go by the criteria which I made students write a few minutes back, you can clearly see that A is positive. Since the sign of A is positive, and AC minus B square is also positive, what can I say? I can say that therefore minus 4 by 3 comma 1 by 3 is a minima, is a point of minima, is a point of minima. And if someone asks you to find the minimum value, just plug minus 4 by 3 and 1 by 3 in this equation. That is going to give you the minimum value of the function. Okay, so this is our answer. We have classified the stationary point minus 4 by 3 comma 1 by 3 as a point of minimum. Okay, let's look at question number 2. Erasing all this off. Let's look at question number 2. Determine the extreme values of the following function. Determine the extreme values of the function z, which is x cube plus y cube minus 3xy. Now, first of all, we look at the first order derivative. So my first order conditions are, so I can also write this as a function of x and y. So my first order condition, del z by del x equal to 0. Let me quickly work that out. Del z by del x is 3x square minus 3y equal to 0. Okay, so this gives me 3x square equal to 3y. 3 and 3 cancel out. I get x square equal to y. And x square equal to y means that x is either plus y or x is equal to minus y. Let me correct myself. I think I wrote the opposite. X square equal to y means what? X square equal to y means the following. It means the following. So let me leave it here only for right now. Let me leave it here. Let's not simplify it. We'll simplify it when the second condition also comes. Let's call this as equation 1. Okay. The second first order condition is del z by del y equal to 0. If I partially differentiate z with respect to y, I treat x as a constant. So 3y square minus 3x equal to 0, which implies 3y square is equal to 3x. Again, 3 and 3 cancel out. I get y square equal to x. Equation number 2. Okay. Now let's do one thing. So what we can do is look at this equation and let's look at this equation. Now, what do we get? So if you look at x square equal to y condition, how can I further write it? So I can write, so if I square both sides of equation 1, squaring both sides of equation 1, I get x to the power 4 is equal to y square. And what is y square? Y square itself is equal to x. So x to the power 4 is equal to x. In the bracket, I can write since y square is equal to x from equation 2. If I take this x to this side, I get x4 minus x equal to 0. If I take x common, inside I get x cube minus 1 equal to 0, which implies that x is equal to 0 or x cube minus 1 is equal to 0, which implies that either x is 0 or x cube minus 1 equal to 0 means x cube equal to 1, which implies that either x is 0 or x cube equal to 1 means x is equal to 1. So we have got the stationary point x is 0 or x is 1. Now if x is 0, y is 0. If x is 0, y is also 0. And if x is 1, then y is also equal to 1. So what are the stationary points I have got? I have got 2 stationary points. So I think I can write here. Therefore, there are 2 stationary points we have got. There are 2 stationary points which are x and y both taking the value 0 and x and y both taking the value. I am revising this again. Del z by del x equal to 0 gave me x square equal to y. Del z by del y equal to 0 gave me y square equal to x. How do I solve this? Look at equation 1. Let us make this y square. How do I make this y square? I square both sides. X square squared up is x4 y square, and y square itself is equal to x. Bring x to this side, I get x4 minus x equal to 0. Take x common, I get this. It means either x is 0 or x cube minus 1 is 0. X cube minus 1, 0 means x cube is 1, and x cube 1 means x is 1. Now, if x is 0 from equation 1, y is also 0. And if x is 1 from equation 1, y is also 1. So, I got my two stationary points. Now, let's classify them. So, I erase all this off. And now let's work out fx. Let's work out a. What is a? Fxx, which is del square z by del x square. If I differentiate this further with respect to x, I get 6x. Okay. What is c? Fyy. This is del square z by del y square. How do I find del square z by del y square? Differentiate this further with respect to y, I get 6y. And b is going to be fxy, which is del square z by del x del y. How do I find this? Look at fx, differentiate this with respect to y, so I get minus 3. So what will ac minus b square be? A is 6x, c is 6y, minus b square is minus 3 square. So it's going to be 36xy minus 3 ka square is 9. So this is my AC minus b square. 36xy minus 9. Okay, now let's look at the signs. So if I erase all this off now, let's look at the signs of A and AC minus b square at these points. So I can now make a table to make it look more systematic. Let me draw a table where I have the points. I have the sign of A and I have the sign of AC minus B square, because these are my deciding factors. So my points are 0, 0 and 1, 1. And A was 6x. So put 0, 0, this is 0. Put 1, 1, it's 6. And AC minus B square is 36xy minus 9. So put x and y both as 0. So this is 36 into 0 into 0 minus 9, which is minus 9. And here I have 36. Here I have 36. 30. Let me write this clearly. This is as follows. 36 into 1 into 1, because x and y both are 1, minus 9. So which is 36 minus 9, which comes out as, which if I calculate 36 minus 9, it comes out as 27, which is positive. So here you can clearly see that my AC minus B square is negative. So I can say therefore 0, 0 is a saddle point, because AC minus B square has come out as negative. And if you look at 1, 1, A is positive and AC minus B square is also positive. So I can say therefore 1, 1 is a minima, is a point of minima. 1, 1 is a point of minima. As per the second derivative test, 1, 1 is a point of minima, 0, 0 is a saddle point. Okay, so I stop in this particular practice lecture. The objective of this lecture was to revise with all students the concept of maxima or minima for functions in several variables, revise the first derivative test and second derivative test, and do 2 practice problems based on this concept. Okay, now in the next lecture, in the next practice lecture based on multivariable optimization, I am going to look at now some economic applications. Economic applications of
multivariable optimization. So in the next practice lecture is going to be very important, students. We are going to look at economic applications of multivariable optimization in the next practice lecture. I hope students have enjoyed this lecture. Any doubts? You can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolofelconomics@gmail.com. This is where I stop in this lecture.